Hello, this is 1.4, the tangent and velocity problems. So in 1.4, we are starting to get into the skin of calculus, talking about quick introductions and some type of applications that we'll see in calculus 1. All right, so in the beginning, I want to talk a little bit about what's called a tangent problem or the property of tangent. Now, I know many of you know tangent as one of the trig function, right? But in this sense, we are going to look at tangent in another definition. Okay, so the word tangent is derived from Latin word tangens or tangens. I have no idea how to pronounce that, which means touching. Okay, and what does that mean? Right, we're very interested in finding what that means. So I'm just gonna do uh, a circle like that. Okay, and what I'm going to do is I'm going to introduce a line that basically touches the circle at a singular point. Right, let's say it's hard to get it to touch at exactly one point right here. Okay, and let me see if I can do a better job. There you go. Okay. So this blue line, that's called this blue line L. Okay. And that's called this point that the line and the circle touching, that's called that point P. Okay. So what we can say about this line L is that this line L is tangent to the point P of the circle. Right. The line L is tangent to the circle at point P. Okay, so this is particularly interesting because this is the only line that can the point at touch the circle at the point P exactly at point P, right? Any other line will be crossing point P in a multiple position, right? For example, this orange line will touch the circle twice going through point P, and then you can introduce another one. Let's say something like that, all right? That also goes through point P, but it crosses the circle at two different points. All right, in that case, the two orange lines are not called tangent, right? So for in this case, the only line that is tangent to point P of the circle is the blue line. So that is very interesting because there can be only one line that cross point P and is tangent to the circle. All right, now let's look at another example, right? This picture, right? We can see that the red line just barely touches the curve C at point P, right? So if you just focus on this area, we can see that the red line only touches the curve at point P, right? But you can say that, oh, okay, maybe it touches the graph here as well, right? But then does that make it a tangent line? And actually, by definition, yes. That's called the red line L as well, right? In different example, that's fine. So L is also considered a tangent line um tangent line of C at at P. Now, but this might raise some question, right? Why can't in the previous example with the circle, why can't we use the orange line as a tangent line? But in this case, the red line can be a tangent line while it crosses multiple points of the curve, right? So the idea is that we want the red line to be only touching point P in this neighborhood, right? With to the left or to the right of curve C, right? Only about this disk region that the red line is the only line crossing curve C at that point. So it's okay if we extend the tangent line and cross the graph somewhere else, right? In this case, it's just an extension of the tangent line, which causes to cross the curve C. So in this case, that's fine because we want the red line to be only touching point P around point P. All right, and to give you a better illustration, we have zoom in around point P. Right, so this red line is the only line that touches the curve at exactly point P. Now, there may be something that's close, maybe something like that, something like this, right? But notice that it crosses P and this point. And since it's too close in the neighborhood, this would not be a tangent, right? And then we can have something like that as well, right? Touches here and point P, right? Therefore, not a tangent line. Right, so a tangent line has to only touch the curve at exactly one point. Now, it doesn't matter if down the road it's going to cross another curve at another place. That's fine as well. But in the neighborhood, we don't want it to cross um, more than one point. Right. So the idea of the tangent curve comes from this idea. Right. Let's say we have a curve, right, and then let's just draw a random line that has to intersect these 2 points. Now we know to draw a straight line connecting 2 points, all we need to do is connect the line like that, right? And let's say I want to move these 2 points closer together like that, right? Then we'll get maybe a line like this. And then the idea of tangent line is if we move this 2 point close enough so that they become 1 point, then what would the line look like? It would be the line that only touches that point on the curve, right? And that's what it's called a tangent line. And actually, if you have a line going through 2 points, this is called secant line. And it's not a coincidence that it has similar names to our trig functions. As later, if we have time, I'll show in class that, how we define a secant line and tangent line. All right, let's look at our first example. We want to find an equation of the tangent line to the parabola y equal to x squared at the point 1, 1. Okay, now in order to write an equation of a line, a straight line, we at least need 2 points, right? Because when we have 2 points, we are able to find the slope of the line by using the slope formula, and then therefore we can use the slope and any point to complete the equation of the line in slope intercept form. Cool. Okay, so the question now is we only have 1 point, right? So it's really hard for us to figure out what the slope is, right? Okay, so here I have a graph from the book. So our goal is to find the equation of the red line, right? The red line is going to be the tangent line going through point P on the parabola y equal to x squared. So the idea is it's impossible for us, well, as of now, to find the exact equation of the red line. So what we can do is we can use the blue line, right, by picking another point on the xy, by picking another point on the parabola, so that we have 2 points and try to see how close we can get by approximating the red line using the blue line. All right, so the blue line, we do that by picking another x value. All right, so let's say, of course, we know point P is 1, 1. Now, let's say to find the second point, I'm going to pick x equal to 2, right? Therefore, y is equal to 2 squared, which is 4, right? So we have another point 2, 4, right? All right. Now we can get the slope, which is rise over run, right? y2 minus y1 over x2 minus x1. That's 4 minus 1 over 2 minus 1, which gives us 3, right? Positive 3. So assuming that this blue line has the slope of 3, right? Well, we know that the red line it is not exactly 3, but it should be close to 3. But how accurate is the slope 3 for the blue line to approximate the red line? Right. So in order for us to be a little more accurate, we don't have to pick 2, right? Maybe we could pick something between 1 and 2. Let's say 1.5, right? And then we get a point right here. Next, we can use this point and P, 1, 1, to try to make another line that will give us a better approximation of the red line. Okay, and by picking our points closer and closer to 1, we will be able to get a better approximation, right? And if we pick 1.5, okay, then the slope between P and 1.5 will be 2.5, which is less than 3, right? Meaning it's going to be closer and closer to the true slope of the tangent line. All right, and by picking some more values, right? If we pick better values for x, I can see that if I pick the x value from 2 and then 1.5 down to 1.1, 1.01, 1.001, notice that the slope tends to decrease, right? 3, 2.5, 2.1, 2.01. And when we are very close to 1, when x is 1.001, we get 2.001. Right, which is very close to 2, right? So maybe from here you might say, okay, maybe the tangent line has the slope of 2. Let's go the other way, right? Instead of picking our points to the right of P, we can pick points to the left of P right here, right? So we can start with 0, right? So 0 would be picking this point and then do a secant line like that, right? So this line will have a slope of 1, but as you pick points closer to 1, right, that's gonna give you a better approximation. Let me use a different color to show you what I'm trying to say, right? Let's say if I pick 0.5, then my tangent line will look like this, which is closer to red than green, right? So our goal is to get as close as possible to the true tangent line, which is the red line. As you can see that when we pick x value very close to 1.999, we get the slope is 1.999, right? So that's very close to 2, I would say, right? But let's be even more dramatic, right? I want to pick, so point P, right? That's the point we want to focus on, the tangent line going through this point. Let's pick another point. Let's say Q is 1.000001, right? And then when we when we square that, let's see what we have. All right, it's approximately 1.00000002. Okay, so the slope would be 1.00000002 minus 1 all over 1.000001 minus 1. Right? And that gives us what? 0.000002 over 0.00000001. Right? And that is exactly 2. Right? But this 2 right here is actually not exactly, this is approximated by my calculator. Right? So you can see that when we are very close to the point P, when our second point Q is very close to point P, right, we get a very nice approximation, right, which is by calculator standard, it's 2 already, right? By looking at, using this P and Q, we already get that the slope is 2, right? The calculator is telling us 2 because it's just so close to 2, it cannot output a value that's closer than what we had above, right? So in this case, we can safely assume that, well, since when we pick Q to the right of P, right? Where 1.001, or when we pick q to the left of p, 0.99999, and so on, both of them are going to 2, right? Going to 2, right? So we can safely say that, okay, maybe the tangent line has a slope of 2 at point P, right? Now that we have established that, we can say that, okay, so slope is 2. Great. For tangent, right? And we just need to find the equation using point P, right? So y is equal to mx plus b, slope intercept form, right? And let's go ahead and plug everything in. So y is 1, m is 2, x is 1 plus b. All right, so we'll subtract the 2 over, we get -1 is equal to b. Therefore, we can say that the tangent line has the equation y is equal to 2x minus 1. Okay. All right. So, let's be a little more specific. Tangent line of y equal to x squared at 1, 1. All right. And next, let me graph this on decimals and show you guys. All right, so I graph this on decimals, right? The red line is our parabola, y equal to x squared, and the blue line is our tangent line at 1, 1, right? So you can see that the blue line and red line get very close together, and you can see that the blue line actually disappears and then appears around x equal to 1, which is the point 1, 1. Right, so from this point on, we can safely say that this is actually a tangent line through the point P, which is 1, 1. Now, I want to show you another interesting picture. Is what if I zoom in at around the point P on decimals, right? And you can feel free to pause the video and give that a try, right? And let's see what happens when we zoom in. All right, so you can see that I zoom in on 1, 1, where the y values are 0.999 and 1.001 per a scale, right? Like that. So you don't see the red line anymore. You only see the blue line, right? Because those two lines are just so close together when the x values are like close to 1, right? And at exactly 1, 1 is where they intersect, uh, where both lines intersect together, and then as soon as we leave that point, the two lines will drift apart again. But the difference between the two lines around the point 1, 1 is just so small, it's so hard to graph on the xy plane, even with a computer. But mathematically, we can actually calculate what the difference is at around this area, right? But at exactly 1, 1 is where they touch. All right, so here I just want to show you guys the idea we're doing, right? Let's say here it's q has x value of 2, here's 1.5, and let's say here's 1.25. Right now, so you can see that as we move the point q closer and closer to the point p, notice that the blue line is getting closer and closer to the red line. Right? That's why we want to pick the points P and Q closer together to get a better approximation. Now you can get as close as you want, right? Because the tangent line, by definition, only touches the curve at a single point P, right? But what we can do here is we can approximate what the equation is, what the tangent line is, by selecting another point Q and make it closer and closer to P. So the blue line here are called the secant lines. Right? So the blue line, these are called the secant line. Right? So basically we are using the secant line to approximate the tangent line. All right, and just interesting definition, interesting fact. A secant line, from the Latin word secans or secans, I don't know how to speak Latin, meaning cutting, is a line that cuts or intersects a curve more than once. Right? And in this case, we have seen a mini example of the blue lines cutting the parabola at 2 points, right? And as they get closer and closer together, the secant line will be more and more like the tangent line. Okay? All right, and here we have 3 graphs. Again, if we pick the point Q to the left of point P, right? So that, and a little closer and closer, right? And you can see that the blue line changes as we move the point Q closer and closer to P, and the line will become more and more like the secant line will be more and more like the tangent line. All right, so let's look at some applications of what we just talked about, which is talking about velocity. Now, about 14 centuries ago, Galileo discovered that distance fallen by any free-falling body is proportional to the square of the time it has been falling. Right, so it was a long time ago, and we didn't have the technology we have today to measure air resistance and wind and all those kind of stuff, right? So this model is for free fall neglect resistance. Okay, and of course, depending on where you are, the gravity will be slightly different, but not by much. But that also can um, have some effect on the time of free falling or velocity. All right, let's take a look at an example. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. All right, so let's do a quick graph. And let's say this is the tower, right? And then right here, height is 450 meters, and then you drop the ball, and let's say after 5 seconds the ball is right here and still falling, right? T equal to 5, and we want to find out what's the velocity. Okay, how fast is the ball traveling downwards at exactly t equal to 5? Now you can think about this. Okay, so maybe at 4.9 seconds the speed should be pretty close to 5, right? um, so velocity at t equal to 4.9 second should be close to velocity at t equal to 5, right? And if you think that, you'll be right, right? But, we can be a little more accurate than that. But let's just use 4.9 for now, right? I'd say we want to find the average velocity. Actually, I'm going to type this one out. All right, so average velocity is given by the change in position over time elapsed. Right, so we're looking at t from 4.9 to t is 5 seconds. Right, now we're going to use the position formula, position function by Galileo. Right, s of t is equal to some constant times t squared. Right, now in this case, let's assume that k is 4.9, right? The constant for k. Right, so our position function s of t will be 4.9 t squared. Right, what does that mean? That means when we plug in s of 4.9, right, I get 4.9 times 4.9 square, which is 117.65, right, meters. Right. And so what this is saying is, when after we drop the ball, after 4.5, after 4.9 seconds, the ball will be traveling 117 and 65 meters. Right. And let's find out what S of 5 is. after 5 seconds. So 4.9 times 5 square, and that's going to be 122.5. Okay, so we have the change in position between 4.9 seconds and 5 seconds. Now, and we also know the time elapsed. We are able to find the average velocity, right? Which is, let's see, 122.5 minus 117.65 over 5 minus 4.9. And let's see what we have here. Minus 117.65 divided by 0.1. Right, I get 48.5 meters per second. Right. So what this is saying is, this is the average speed between 4.9 seconds and 5 seconds. Now, 4.9 seconds and 5 seconds, they are very close together, right? Just by a 0.1 second difference, right? So we know that the average velocity of the ball between 4.9 seconds and 5 seconds is about 48.5 meters per second, right? But if you want to be more accurate, of course, instead of 4.9, you can pick 4.99, you can pick 4.999, or you can also pick to over 5, right? 5.1, 5.01, 5.001, and see what you can get, what you can get to, right? How close you can get to the actual speed. All right, so here I have a table. Is if you use oops, if you use 4 point, if you use 5.1 and 5.05, 5.01, and so on, you can see that the speed is very close to 49, right? As we get closer and closer to 5, the average velocity getting very close to 49. Now, can you conclude that the speed of the ball at exactly 5 seconds is 49? Maybe, right? But you might need to show a little more, right? For example, instead of 4.9 up here, we can pick 4.99, 4.999, and see if we get closer and closer to 49 meters per second, right? And in fact, actually, you can feel free to give that a try to see if you can get the value of 49 meters per second. And from that, we can say that, okay, we have shown after a short period of time, the average velocity is becoming closer to 49 meters per second, right? Based on our calculation from both sides, right? It's getting very close to 49. And here, the instantaneous velocity when t is equal to 5 is defined to be the limiting value of these average velocities over shorter and shorter period of time, right? So what we are looking at here, right, when we pick t closer and closer to 5, these are called the limiting velocities, or I should say limiting values, right? Because we're getting very close and close to 5, but exactly, we cannot use 5 because think about drawing tangent line, drawing secant line, right? There has to be 2 points and some difference between them. Same thing with the velocity example that we're looking at, right? So the instantaneous velocity means the exact velocity at t equal to 5. Okay, so by taking the limiting value, we are able to approximate the instantaneous velocity with very small error, right? Depending on how close you get to t equal to 5, right? Thus, it appears that the instantaneous velocity after 5 seconds is 49 meters per second. Now, from the two parts that we looked at, right, starting with a tangent line and then the velocity, instantaneous velocity, or averaging velocity. Now, these two ideas are a gateway into calculus, because in calculus, this is where the idea of calculus comes from, right? We want to get a better approximation at exactly that point. But is there a way for us to find the exact value without having to do this many calculation, right? By experiment, right? Is there a way that we can do that without experiment? And the answer is yes. And that is what we're going to see in this class. Okay, and more interesting topics will come in, but this is just the beginning, right? Think about limiting values, right? How close can you get to be very close to the exact value? Okay, all right. And thank you very much. I know this can be a little confusing for some of you, but don't worry, we will talk more in class, and I'll see you soon. Thank you guys very much.